And the last talk of this session is by Martina on towards composable proofs of cache coherence protocols.
So good afternoon, everyone. I'm Martina Camaioni, and this is a joint work with Yann, Tz-Ching, and Thomas, and we are part of the same laboratory at EPFL. So the main research question behind this work was the following. Can we find a simple and more trackable way to prove correctness of complex protocols using interactive theorem provers? As probably some of you know, when we use interactive theorem provers as Lincock or others, these are really useful tools to prove complex protocols. Why? Because they allowed us, for example, to reason with parametric setting on the abundant state. However, they usually required a lot of human interaction, and this leads to proofs that are really long, takes a lot of time to be complete, and not so much reusable. So for the subject of this project, we decided to focus on a complex hardware problems, cache coherence protocols. Cache coherence protocols are already proved in literature using interactive theorem provers. However, this proofs leads to really long proofs that can take 2 years to be complete. Why? One of the main challenges behind this is the invariant discovery. So usually the user have to come up with hundreds of properties to describe cache coherence protocols. So in this talk, we propose our solution that is like, we discovered that leveraging the inert structure of cache coherence protocols, in particular the local structure, we are able to discover an invariant with much less properties, so it's much more easy to discover. And moreover, we also discovered that cache coherence protocol have we can decompose it, and this leads to proof that are much more reusable. So first of all, why we need cache coherence protocols? So in general, we know that access the main memory is an expensive operation, so we would like that our CPU perform the load store operation not directly to the main memory, but to a local memory that we call cache. However, we need some coordination between different cache, and this is usually done by the parents, because we want to ensure that the memory is coherent. What it means, intuitively, this means that we want that these local caches and the memory behave like as central memories. So how the cache look like? The cache is usually composed of different cache lines. Each cache line have an address, a value, and a state. For the cache coherence protocols that I will present you today, this is MSI because the state can be M, it's a modified state. So in this case, we can perform read and write operation directly on the cache. Then we have the shared state. In this case, we can just perform read operation on the cache, but for the write operation, we have to go back to the main memory. And then we have the invalid state. In this case, we have to go to the main memory to do any read and store operation. So let's analyze, for example, an example to just give you an intuition of how this works. In this case, we have just one cache line, so we don't care about the address, and we have the green cache that is in a modified state with the value 2, and the blue cache that is in an invalid state, and we don't care about the value in this case. So the blue cache wants to perform a load operation. We cannot do it straight away, so the cache have to request the permission to upgrade to the S state to the parents. The parents cannot respond immediately to the blue cache because it doesn't know what is the last value written, because the green cache, you have the modified state, so it can update its value. So what it does, it asks to the green cache to invalidate itself. So the green cache does this and say, okay, the last value that I written in this case was the value 2. The parents can finally now update the memory with the last value written and responds to the blue cache and say, okay, now you have the permission to go to the S state with the value 2. And finally, we're able to respond to our load request. So the question now is how do we define the correctness properties of a cache coherence protocols? As a bit anticipated you before, we wanted the protocols to behave like a centralized memory. So in a centralized memory, we don't have caches, and the load and store operation are performed directly to the main memory. So one key property of a centralized memory is that it ensures coherence. What does it mean? It means that the load operation returns always the last value written. So we would like that also our cache coherence protocols, and this is why it's called coherence, ensure coherence properties. So in order to do that, some configuration must be unreachable in a cache coherence protocols. Why? Because, like, for example, let's analyze this configuration in which we have like the green cache in M in a modified state and the blue cache in a shared state. Now the green cache wants to perform a store operation, it can, because it's in a modified state, so we have that the green cache store, for example, the value 3. Now the blue cache wants to perform a load operation, and it can, because it's in a shared state, but like he's able to read like just the value 2, that is not the last value written in this case, so we want that he's be able to read the value 3. So how do we prove that SM are unreachable configurations? In order to prove this, usually like you need a long and difficult invariant. Why? For two main reasons. So first of all, because cache coherence protocols are complex protocols. What I didn't tell you before is that the parents is not just a coordination between different caches, but like he also have its own state. And it keep track on what is the beliefs that you have for the state of the other cache. And this is like difficult because the cache coherence protocol have a distributed nature, right? So like it doesn't know with the certainty which state the cache are. It just have to guess. For example, in this case, if we have like the green cache that the parent think that is in M, but this green cache wants to invalidate itself and go to I, the parents not yet, doesn't yet analyze the signal, is not update, it cannot update its beliefs. Another problem is that when we want to usually define global invariants, like the one that we care about, that means that two caches cannot be in MS simultaneously, usually we need to state global properties. So for example, we can say, okay, if we don't want that two caches are in MS simultaneously, we don't want that the parents send an OK to go to M and an OK to go to S simultaneously to two different caches, right? And this is like a global properties because it requires like to see the system in its globality. So actually, these properties cannot prove it in isolation, and usually require a loop, and this is like the user work to like say, okay, to prove these properties that we care about, we need to add new properties, and so on and so forth, until our invariant become an inductive invariance. So global invariants consist of many unstructured properties that must be manually identified by the user. The key contribution of this project is realize that actually we don't need any global invariants. So in order to prove the correctness of cache coherence protocols, we just like need to focus our attention on the subunit cache parents. Intuitively, why this is the case? Because even if the parents believe is not update all the time, this is enough to characterize our system. So only focus on the parents' beliefs, a single cache state, and signal between a parents and a single cache. This is enough to prove correctness. And this is particularly interesting if you think about that in general we have a parametric setting. So I present you a system with only two caches, but we can have like n number of caches, right? So instead of like write global invariants that they talk about all the different channels from different caches, it's just sufficient to like focus our attention on this like subunit cache parents. Okay, so now the question is how do we write the correct local invariants? And we actually discovered that this local invariance is much more structured than what we think, because we discovered that to write it, the local invariance is sufficient to ensure 5 different classes of properties. So the first one is what we call relation between signal, that state that some signal cannot simultaneously exist in the cache parents and in the parents cache channel. So in the case, in this example, for example, we cannot have a response M from the parents to the cache and simultaneously a response I in the other channel from the cache to the parents. Then we have what we call signal uniqueness that say all the response signals should be unique. So we cannot have, for example, two response M. Then we have another, the third class that is over-approximation. So I anticipate you a bit before, and I told you that the parents can, is not only update the beliefs that they have on the cache, but we always have to ensure that the parents believe over-approximate the real cache state. So in this case, if the cache is in M, the parents should think that the cache is in M. You cannot think that the cache is in an invalid state, for example, or in a shared state. So then we have the fourth classes, that is conflict configuration, that say that the parents believe that at most one cache can be in M. And finally, we have like the last one, the signal to state, that relates like a response signal, solely response signal, to the cache state and to the parent's case state. In this case, like we have that if we have a response M from the parents to the cache should be in I, and the parents should think that the cache is in M. Okay, so cool. So if we apply these 5 different classes to our MSI, we realize that we just need the 2 properties of the type relation between signal, 4 of the signal uniqueness, 3 over approximation, 2 conflict configuration, and 4 signal to state. So with a total of only 15 properties, we are able to prove the correctness of our MSI protocols, compared to like hundreds of properties of the state of the art. What is significantly cool is that a local invariance of only 15 properties, we are able to prove global correctness property as the one that like we care about, that like 2 cache cannot be in MS simultaneously. So ultimately, with a local invariance, we prove it in Lean for MSI that is coherence, that is like ensure the correctness. Okay, so we discovered that locality significantly reduced the size of invariance necessary to prove correctness. Moreover, we discovered that we can apply this taxonomy not only for MSI protocol, but also for SI and MI subprotocol. So like in SI protocol, the state can be only S and I, and we can perform only load operation. In the MI subprotocol, instead, the state, we can perform both load and store, but the state can be only M or I. We don't have a shared state. So why do we care to prove also the correctness of these other subprotocols? Because like this is interesting in if we want to prove a slightly different version of MSI protocols. So actually what we did is not prove like straightforward that our MSI protocols refine a central memory, as is usually done. But we first discovered that we can do this proof. So we can prove that MSI is just a refinement of a combination of 2 small subprotocols that are SI and MI. And then we prove that SI plus MI refine a central memory. So, so we discovered that actually MSI at each point in time can be described as either MI or a size system, in which if you think about the MI and the size system, they have in common the high state, right? When all the caches are in I. And in this case, we can switch from like one word, one protocols to the others. So why this is interesting? Because modularity helps in building reusable proofs. Let's suppose that now we want to prove a slightly different version of MSI that we call MSI prime. Instead of proving that MSI refine a central memory, as usually is done, we have to prove that MSI refine SI plus MI system, and then that MSI plus MI system refine a central memory is already proved, so we don't have to change. And like do these changes much more easier because we go to an intermediate system instead of doing the whole proofs. So our MSI prime, usually it's a realistic implementation. Instead, we design our combination of SI plus MI protocols allows much more of non-determinism behavior. So for example, in SI plus MI protocols, we can request M and request M even without any preconditions, so without any store or load request. So why we do this? Because in this way, then it's trivial, like proof that, for example, our MSI protocol in which we say, okay, we request S, if we have a load operation, refine SI plus MI, in which we are able to request S even without any load operation. And the cool thing is that then if we change MSI and we say, okay, let's assume that we want to prove MSI prime, in which for a load we request M instead of S, is still refined to the same SI plus MI system, because in SI plus MI we can still like request M without any preconditions. So we can reuse the whole proof without changing our composition of SI plus MI system, because we are allowed much more non-determinism there. So to summarize, during this project, we discovered that locality leads to smaller invariants, that we also able to classify this smaller invariant using the taxonomy that provides structure to locality. We also see how modularity enables more trackable proofs, and non-determinism allows building reusable proofs. In the paper, we also extend like this to multi-address MSI protocols. The question now, a cool research question can be, can we apply this concept of locality and modularity also to other protocols, for example? So I'm done. Thank you for your attention. Fantastic.
Thank you very much, and we have time for a few questions.
Thank you. So I'm not as familiar with the verification of protocols, but it seems to me that the thing that you exploit is this notion that the parent really has an accurate over-approximate view of what its children are doing in order to be able to get from the local property to the global property.
Yeah, so they don't have exactly the perfect view, but they have an over-approximation on that, and this is enough to leverage the correctness, exactly.
So was this like a known technique that you're exploiting? Do you think this generalizes nicely to any other kind of graph protocol where some node has some sort of over-approximate view of all the other nodes are doing?
Yeah, like this was not done before, so like we kind of capture like an inherent property of cache coherence protocols. And like, I don't know if it can be generalized, but I'm thinking that, for example, for distributed protocols in which maybe sometimes we have a leader that have more information, maybe we can apply something similar. And because having this local invariant is much more an advantage because they are much smaller, because the system is much more smaller, right? So it's easy come up with like 10 properties that describe a smaller system instead of 100 for a full system. So this is an interesting research direction.
So cache protocols are a really nice target because they're tricky and important, but also a super annoying target because the real high-performance cache protocols tend to be much more complicated and also confidential. So talking to people in IBM about what they do, some of the details of that are public. And they have all kinds of states and all kinds of different messages between states, which are tricky to imagine dealing with. So I wonder what, I've not been paying attention to that recently. I don't know what is known and what you can feasibly aim to do sort of in the public literature beyond things like MSI and MESI and whatnot.
So you mean for protocol that like you don't know the implementation, or like you know?
Well, there are a bunch of fancier implementation techniques which are somewhat known, and some of them are described in patents, but you can't find a description of the IBM Power 9 protocol in detail. But it might be that that you can see the ideas in the design of them and know whether this kind of thing would be applicable. Yeah, maybe if I can have abstract at least like implementation of that, I can try to apply the same ideas. Like, and I suppose my point is really there is a whole world of much more complicated cache protocols that is annoying to look at, but which one can look at some aspects of. Now maybe they also have some inherent structure that we can take advantage. So like the most takeaway of this work is that like sometimes instead of go straight forward to the problems and try to come up with invariants, like looking on like what is the inherent structure of the problem, the protocols that we can take advantage in this case was, for example, these locality properties, simplify a lot like the proofs. So maybe there will be like slightly different concept like that can still simplify the proofs. And that would be a happy world. Yeah.
Do we have other questions? So I have a question. In your refinement, you were refining between MSI and MI plus SI. Do you have an intuition if you added more states to this, right? So MESI or MOE, SI, or so on. Do you expect that you would have similarly an OI and EI and then the refinement will work?
Yeah, I didn't prove it, but I expect that if you add a new state, and like you can still come up with this diagram, let's say, so in which you can still say, maybe now you have a new state, O state, and whatever, but it should be still like go to I, so you can come with these subprotocols. This part of the proofs like are reusable, right? You don't have to prove it again, and you just have to add that like part. So this is also a cool thing of like why decomposition can like lead to reusable proofs.
We have time for one more question. Well, I have one more question. So you are modeling the behavior of these cache coherence protocols, but there's also a lot of work on verified implementation of processors and cache hierarchies now. Can you imagine connecting these? Would there be difficulties in connecting this with actual hardware implementations, assuming you have the right models for the hardware itself?
For a cache coherence protocols?
Yeah, could you verify like an actual circuit that implements this, rather than just a model of how this works?
I mean, we can extract like some code that runs and then like, but yeah, like, I don't know, I did only on like abstract implementation, so.
Cool, so it sounds like there's good follow-up work there. All right, well, let's thank the speaker again and every speaker in the session.